Now, question number 6, exercise 9.6. The given differential equation is x dy upon dx plus 2y is equal to x square log x. Obviously, this is not in standard form because in standard form of linear differential equation, coefficient of dy upon dx should be 1. So, in order to bring it into standard form, we need to divide both sides of this equation by x. So, dividing both sides by x, we get dy upon dx plus 2 1 upon x y is equal to x log x. This is now in its standard form, and that would be equation number 1. Now comparing this equation with dy upon dx plus py is equal to q, where p and q are some constants or functions of x. So we have p is equal to 2 upon x and q is equal to x log x. Now let's find integrating factor. So integrating factor in that case will be e raised to the power integral p dx. That will be e raised to the power integral 2 upon x dx, and that is e raised to the power 2 should be taken out as constant coefficient, integral 1 over x dx. That is equal to e raised to the power 2. Integral of 1 upon x with respect to x is log x. So log x. Now using logarithmic property, this 2 can be taken to the power of x. We have e raised to the power log x square. And since e raised to power log eliminate each other, and we have only x square. So integrating factor is x square. That will be equation number 2. Now this is linear differential equation, so its solution will be format of y into integrating factor is equal to integral q into integrating factor dx plus c. Substituting in this equation the value of integrating factor and q, we have y into integrating factor, we have found x square is equal to integral, and q we have in this equation q is equal to x log x. So write down x log x, x log x, integrating factor which is x squared, so write down x square dx plus c. So simplifying right hand side, we have x into x square x cube log x dx plus c. Now proceeding from this step, now on the right hand side, if we observe the type of integrand, this is the integrand which is integrated with the help of integration by parts, because there are the product of two functions x cube and x log x, and no function is the differential of the other one. So ultimately we need to use integration by parts. But according to Eilert rule, sequence of the functions is not correct. Log x should come first. So let us change this, integral log x into x cube dx plus c. Now considering log x as first function, as x cube as second function, we have to integrate it by parts. So on the left hand side it's the same, y into x square, we have integrating by parts first function as it is log x, and integral of the second one, that is x to the power 4 upon 4, minus integral as a whole, differential of first, that is differential of log x which is 1 over x, and integral of the second x to the power 4 upon 4 dx plus c. So y into x square is equal to, this term may be written as x raised to the power 4 upon 4 log x, and here this x will cancel one power from numerator, so the power remains 3, and minus this 1 upon 4 is constant coefficient, should be taken out of the integral, 1 upon 4. Inside the integral we have only x cube dx plus c. So that is equal to x raised to the power 4 upon 4 log x minus 1 upon 4. Integral of x cube will be x raised to the power 4 upon 4 again plus c. So simplifying this, we have x raised to the power 4 upon 4 log x minus x raised to the power 4 upon 16 plus c. Finally, we have to transpose this integrating factor, which is x square, on the left hand side to right hand side. So it will divide each and every term. So we have y on the left hand side, and if the first term is divided by x square, that will divide x raised to power 4, and we have x square in the numerator upon 4 log x, and minus, if we divide second term by x square is left in the numerator and 16 in denominator, x square minus upon 16, plus c is divided by x square, we have c upon x square. So this is the required solution of the given differential equation. Now the seventh sum of the exercise 9.6 is x log x dy upon dx plus y is equal to 2 upon x log x, and we need to find the solution of this differential equation. So obviously, as the differential equation is of the form linear differential equation, but the coefficient of dy upon dx is not unity, so to bring it into a standard form, we need to divide both sides of the equation by x log x. So dividing both sides by x log x. If the first term is divided by x log x, this x log x will be cancelled by this x log x, and we have only dy upon dx, plus if the second term, which is y, and it is divided by x log x, so we have 1 upon x log x into y. If third term is divided by x log x will cancel log x, and x will multiply this x because it is already in the denominator, so we have 2 upon x square. Let it be equation number 1. Now comparing with dy upon dx plus py is equal to q. We have p is equal to 1 upon x log x, and q is equal to 2 upon x square. Let it be equation number 2. Now let's find integrating factor, which is equal to e raised to the power integral p dx. So we have that is equal to e raised to the power integral 1 upon x log x dx. This is the case of integration by substitution, because in differential of log x is exactly 1 upon x, which is already here, 1 upon x. So let us assume log x as u. Differentiating, we have differentiating this equation with respect to x, we have 1 upon x dx is equal to du. So if we replace log x by u, 1 upon x dx will be replaced by du. So we have integrating factor is equal to e raised to the power 1 upon u du. And as you know, integral of 1 upon u with respect to u will be log u. So we have e raised to the power log u. E raised to the power log u is equal to u, because as per rule e raised to the power log eliminate each other. We have only u, and u we had assumed as log x, so write u as log x again. Ultimately integrating factor is equal to log x. Let it be equation number 3. Now substituting the value of integrating factor and q in the equation, y into integrating factor is equal to integral q into integrating factor dx plus c. We have y into log x is equal to integral 2 upon x square, because q is equal to 2 upon x square from equation number 2, and integrating factor again log x plus c. 2 can be taken out. We have integral 1 upon x square, which may also be written as x to the power minus 2 log x plus c. Now this is the case of integration by parts, but the sequence of the function should be changed according to Eilert rule. Log x should be first function and x to the power minus 2 should be second function. So we need to change the sequence. Integral log x into x to the power minus 2 dx plus c. So taking log x as first function and x to the power minus 2 as second function, integrating by parts, we get 2 as constant coefficient bracket first function as it is into. Integral of x is to the power minus 2 is obviously x is to the power minus 1 upon minus 1 minus integral as a whole, differential of first function which is 1 over x, differential of log x is 1 over x, and integral of the second, that is again x is to the power minus 1 upon minus 1 dx plus c is equal to 2 bracket minus x is to the power minus 1 may be written as minus 1 upon x and log x as it is, and here this minus 1 make this minus positive, so plus integral, and this x is to the power minus 1 may be written as 1 upon x, so 1 upon x into 1 upon x becomes 1 upon x square dx close plus c, that is equal to 2 integral minus 1 upon x log x plus integral. To integrate 1 upon x square, we need to write it as x is to the power minus 2 dx plus c. So 2 integral minus 1 upon x log x. Integral of x is to the power minus 2 is x is to the power minus 1 upon minus 1 bracket close plus c. So if we open up the bracket, we have minus 2 upon x log x. This minus makes this plus minus, minus 2 will multiply this term 2. So minus 2, and x is to the power minus 1 may be written as 1 over x plus c. Finally, we have to transpose this log x, which is on the left hand side, with y to right hand side, leaving y alone on the left hand side. That is equal to y is equal to, and if we divide first term by log x, we have only minus 2 upon x, and if we divide second term by log x, we have minus 2 upon x log x, and then c divided by log x. Though this is our final answer, but we may simplify a little bit further. So let's do it. Y is equal to, out of these two brackets, obviously minus 2 upon x is common, so we may take minus 2 upon x common, leaving inside 1 plus 1 upon log x and plus c upon log x, or we may write it as y is equal to minus 2 upon x, taking LCM log x inside, we have log x plus 1 upon log x plus c upon log x. So this is the required solution of given differential equation. Eighth sum, the given differential equation is 1 plus x square dy plus 2xy dx is equal to cot dx. First we need to divide both sides of this equation by 1 plus x square dx. And why we are doing so? Because we need dy upon dx. So if we divide whole equation by dx, we get here dy upon dx, which is required, and the coefficient of dy upon dx must be unity. So we need to eliminate 1 plus x square from the coefficient of dy upon dx. So both purposes are solved if we divide both sides of this equation by 1 plus x square dx. So if we divide first term by 1 plus x square dx, 1 plus x square will be divided by 1 plus x square one time, and dy is divided by dx, so we get only dy upon dx. In the second term, if we divide this by 1 plus x square dx, dx will cancel dx, and 1 plus x square will be written in the denominator of 2x, so we have 2x upon 1 plus x square y is equal to, if right hand side is divided by 1 plus x square dx, so dx will divide dx, and we get cot x upon 1 plus x square. Now this is a standard form of linear differential equation. Let it be 1, comparing with dy upon dx plus py is equal to q. So we have p is equal to 2x upon 1 plus x square, and q is equal to, q is the right hand side of the standard differential equation, and here on the right hand side we have cot x upon 1 plus x square, so q is equal to cot x upon 1 plus x square. That will be equation number 2. Now let's find integrating factor, which is equal to e raised to the power integral p dx. So that is equal to e raised to the power integral 2x upon 1 plus x square dx. Obviously, if 1 plus x square is taken as t, 2x dx becomes dt. So we have 1 upon t dt, and integral of 1 upon t with respect to t is log t, and we have e raised to the power log t, and when we put the value of t as 1 plus x square according to our assumption, we have e raised to the power log 1 plus x square. So directly we may integrate it as e raised to the power log 1 plus x square. Now e raised to the power log eliminate each other, and we have only 1 plus x square. That will be equation number 3. Now we have to substitute the value of integrating factor nq in the equation. Y into integrating factor is equal to integral q into integrating factor dx plus c. We have y into integrating factor is equal to 1 plus x square, so y into 1 plus x square is equal to integral, and q is equal to cot x upon 1 plus x square, so cot x upon 1 plus x square dx plus, and integrating factor is 1 plus x square, so 1 plus x square dx plus c. This 1 plus x square is cancelled by this 1 plus x square, and we are left with integral cot x dx plus c. Integral of cot x is log sin x plus c. Now finally transpose 1 plus x square to right hand side, we have y is equal to log sin x upon 1 plus x square plus c upon 1 plus x square. Because transposing 1 plus x square, it will divide both the terms. So we have log x sin x upon 1 plus x square plus c upon 1 plus x square. And this is the required solution of the differential equation. Ninth question is, solve the differential equation x dy upon dx plus y minus x plus xy cot x is equal to 0. So x dy upon dx plus y minus x plus xy cot x is equal to 0, or x dy upon dx, collecting the terms having y, that is this term and this term, plus y plus x cot y plus x y cot y plus x y cot x, and transposing the term having no y, that is this term minus x. So on transposition it becomes plus x on the right hand side, dy upon dx. Out of these two terms we may take y common. So inside the bracket we have 1 plus x cot x y outside as common is equal to x. Now to write this equation as a standard form of linear differential equation, we need coefficient of dy upon dx as unity. So in order to do so, we have to multiply both sides of this equation by 1 upon x, or in other words, we should divide this equation by x. So dividing by x, we get dy upon dx plus 1 upon x plus cot x y is equal to 1. Let it be equation number 1. Now this is in a standard form, dy upon dx plus py is equal to q, where p and q both are some function of x or constants. So comparing with dy upon dx plus py is equal to q, we have p is equal to 1 upon x plus cot x, that will be equation number 2, and q is 1, that will be equation number 3. Now proceeding from this step, first we need to find out integrating factor. So integrating factor is equal to e raised to the power integral p dx, that is equal to e raised to the power integral 1 upon x plus cot x dx, that is equal to e raised to the power integral of 1 upon x is log x plus integral of cot x is log sin x. As we know, the logarithmic property is log m plus log n is equal to log m into n. Using this identity, we may write log x plus log sin x as log x sin x. Now, by the property e raised to the power log eliminate each other, so leaving x sin x only, we have x sin x. Let it be equation number 4. Now, for finding required solution of the given linear differential equation, substituting the values of integrating factor and q in the equation, y into integrating factor is equal to integral q into integrating factor dx plus c. We get y into x sin x is equal to integral q is 1 from equation number 3 and integrating factor is x sin x dx plus c. Now on the right hand side we have integral x sin x dx plus c. Obviously this is the case of integration by parts. So let's integrate this by integrating by parts. X is the first function and sine is the second function. So applying integration by parts, first function as it is, integral of the second function, that is sine x, integral of sine x is minus cos x, minus integral as a whole, differential of first, that is 1, differential of x is 1, and integral of the second, again minus cos x dx plus c, that is equal to, if you open up this bracket we get minus x cos x, and this minus multiply and becomes plus cos x dx plus c. Now proceeding from this step, on the left hand side we have y x sin x, so y into x sin x as it is, and on the right hand side we have minus x cos x, and after that plus integral of cos x, as we know well integral of cos x is sin x, so it becomes sin x and then plus c. So finally the right hand side has been integrated, and after that we need to transpose the coefficient of y from left hand side, leaving y alone on left hand side, and on the right hand side every term is divided by x sin x. So we have minus x cos x plus sin x plus c divided by x sin x. This is the required solution of the given differential equation, though we may also write it in different form, splitting all these terms. Y is equal to x sin x will divide each and every term, so if we divide the first term, x will cancel x and cos x upon sin x becomes cot x, plus in this term sin x will be cancelled by sin x, leaving 1 upon x only, and plus, and here if we divide c by x sin x, so we get c upon x sin x. 1 upon sin x is cosec x, so we may also write it as c cosec x over x. So this is the required solution of the given differential equation. You may write any one of these two solutions. Now the 10th sum is x plus y dy upon dx is equal to 1. Obviously we need to transpose x plus y to right hand side first. So we have dy upon dx is equal to 1 upon x plus y. After that We have to take the reciprocal of this equation. So we have dx upon dy is equal to x plus y. Now transposing x to left hand side, we have dx upon dy minus x is equal to y. Let it be equation number 1. And obviously this is the standard form, dx upon dy plus p dash x is equal to q dash, where p dash and q dash are some functions of y or constant. So we get p dash is equal to minus 1, which is the coefficient of x over here, minus 1, and q dash is equal to y. That will be equation number 2. Now find integrating factor, which is in this case e raised to the power integral p dash dy. Remember, in the standard form of dy upon dx plus py is equal to q, integrating factor is e raised to the power p dx, and in the second format of linear differential equation, dx upon dy plus p dash x is equal to q dash, integrating factor is e raised to the power integral p dash dy. Now proceeding from this step, integrating factor is equal to e raised to the power integral p dash is minus 1 dy. So e raised to the power integral of minus 1 with respect to y is minus y. Let it be equation number 3. Now substituting the values of integrating factor and q dash in the equation, x into integrating factor is equal to integral q dash into integrating factor dy plus c, which is the standard solution for a linear differential equation of type dx upon dy is equal to dx upon dy plus p dash x is equal to q dash. So we have x into integrating factor is e raised to the power minus y, e raised to the power minus y is equal to integral q dash from equation number 2, it is y. So y integrating factor again e raised to the power minus y dy plus c. Obviously this is the case of integration by parts. So first function as it is, integral of the second function becomes e raised to the power minus y upon minus 1 minus integral as a whole differential of first with respect to y, so differential of y with respect to y is 1, and integral of the second same e raised to the power minus y upon minus 1 dy plus c, that is equal to minus y e raised to the power minus y. This minus and this minus become plus integral e raised to the power minus y dy plus c. So finally minus y e raised to the power minus y and integral of e raised to the power minus y again, so plus e raised to the power minus y upon minus 1 plus c. By the change of scale property, as the coefficient of y is minus 1, so we need to divide integral of e raised to the power minus y by minus 1 is equal to minus y e raised to the power minus y, and this minus into plus becomes minus e raised to the power minus y plus c. Finally, we need to transpose e raised to the power minus y from left hand side to right hand side, leaving x alone. On left hand side we have x is equal to, and e raised to the power y will divide each and every term. So if we divide first term by e raised to the power minus y, we get only minus y. If we divide second term by e raised to the power minus y, we have minus 1, and if we divide third term by e raised to the power minus 1, we get c upon e raised to the power minus y, or x is equal to minus y minus 1 plus c, and 1 upon e raised to power minus y may be written as e raised to power y, so e raised to the power y. Now proceeding from this step, for the sake of clarity, I am going to write down this equation as it is again. So we may leave our answer over here because this is complete, though we may write this in different forms. Transposing minus y and minus 1 to left hand side, we may write it as x plus y plus 1 is equal to c e raised to the power y. So this is the required solution of given differential equation.